chapters. One is crystallography and the second one is crystal imperfections. I'll share the screen first. Is this visible, students, presentation?
Sir, is PPT enough to write a SEM exam, sir? Otherwise,
Yes,
any
what?
additional?
No, this is, I gave this in such a way that it is enough for as per the examination is concerned. Okay.
Okay. Okay, sir.
So the first chapter is crystallography. So in this you have types of crystal systems, Bravais lattices, and 3-4 definitions are there, like space lattice, basis, and unit cell. Then you have lattice planes and Miller indices, and interplanar spacing for a cubic system, Bragg's law, powder diffraction method. So in this, if you see, in general, the essay questions will be types of 7 crystal systems. Describe 7 crystal systems you may get as an essay question. Similarly, Bravais lattices and a powder diffraction method. These 3 generally you will be getting as essay questions. And for short answers, a problem on Miller indices, identifying a space, lattice plane, or determination of Miller indices, sometimes you may get, and sometimes Bragg's law also. Like that, you can't take, can't guess anything for a short answer, but generally for essay questions, these are the 3. So I'll review briefly the chapter. You listen carefully. Then with this PPT, I think it will be easy for you to go through this chapter. And crystalline materials, the solids are classified into crystalline solids and amorphous solids. If the atoms or molecules arranged periodically in a regular periodic manner, it is a crystalline solid. And if the atoms or molecules are not arranged in a regular manner, they are called amorphous solids. So we'll be discussing here only crystalline materials. So the study of geometrical and other physical properties of crystalline solids using X-rays, photons, neutron beams, electrons, etc. It is called as crystallography. These definitions also better just you remember. What is lattice? The periodic arrangement of atoms in a crystal is called as lattice. So the array of points in space, it is the, actually you should write this one. Space lattice, it is defined as the infinite array of points in 3-dimensional space, so that every point has identical environment. Then it is called as a space lattice. So if you imagine a space, and in this you identify a number of points which are having identical environment, these are imaginary points only, then this is called as a space lattice. Infinite array of points in 3-dimensional space, in which every point has identical environment, then it is called as a space lattice. With this diagram you should write. Actually, if suppose for 2 marks it is given define space lattice and basis, you should write this definition with this diagram. And this is for understanding sake only. So this is a lattice plane, lattice lines, and lattice points. If you go through this, you can understand. And this definition basis also. So a group of atoms, identical atoms or molecules which are identical in composition, arrangement, is called as a basis. So actually it is a composition of a material. So the association of a basis with lattice will give you the crystal structure. So the space lattice, these are imaginary points in space, and basis, it is a combination of composition of identical and similar molecules or atoms associating. That means each identical unit should be associated at this point, so that the crystal structure will be coming. So lattice plus basis, this gives you the crystal structure. So this definition also you should remember. And third one is unit cell. So the fundamental geometrical pattern which on translational repetition will give you the actual crystal structure. So unit cell is the smallest block or geometric figure from which the entire crystal is built by the repetition in 3 dimensions. So along x-axis, y-axis, z-axis. So the same fundamental pattern is repeated so that it builds the given crystal structure. So the lattice parameters, there are 6 lattice parameters. A, B, C are the primitives which are sides. A is the primitive along x-axis, B is along y-axis, and C is along z-axis. And alpha, beta, gamma are the interfacial angles. So these six parameters will decide the geometrical pattern of a unit cell. So where it cuts x-axis, y-axis, and z-axis, and what are the interfacial angles. So these are the lattice parameters involved for a unit cell. So space lattice, an infinite area of points in space such that every point has identical environment, is called as space lattice. And the basis is, it is a composition of identical and unique molecules or atoms, and lattice plus basis will give you the crystal structure. Whenever you associate this unique composition with the lattice only, the crystal structure will be built. And unit cell, it is the fundamental geometrical pattern which on translational repetition will give you the actual crystal structure. So these are certain examples. And coming to the essay questions, the 7 crystal systems. So the 7 crystal systems, it is given in this table. So depending on the relation between the primitives, that is A, B, C, and interfacial angles, the crystal systems are classified into 7 categories. Cubic crystal, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral or trigonal, and hexagonal. So these are the 7 crystal systems, and you should remember this also. If you take a cubic system, all the 3 sides are same. A is equal to B is equal to C. Interfacial angles are also same, which are mutually perpendicular to each other. So alpha is equal to beta is equal to gamma, that is 90. And you should write the fundamental structure. So unit cell structure also you should draw, and with some examples. There is no concept in explaining this. So you should remember this, the 7 crystal systems, and the relation between primitives and the relation between interfacial angles, and with some example. And also you should draw the unit cell structure, then you will get full marks. So the unit cell structures are given in Bragg lattices that I'll show. So this is drawing a unit cell, that in the class I have shown that. Yes. So 7 crystal systems is one question. All cubic crystal, triclinic, monoclinic, tetragonal, rhombohedral, you should write the names, and the relation between the primitives, A is equal to B is equal to C, etc. And also interfacial angles, alpha is equal to beta is equal to gamma, and the relation. Then write the example and draw the unit cell structure of cubic crystal unit cell, orthogonal or rhombohedral, like that. You should practice this. So this is one question. And the second one, Bragg lattices. This may also you may get. Describe Bragg lattices. So there are several ways to describe a lattice. So according to Bragg, there are only 14 distinguishable ways of arranging lattice points in 3D space, so that the environment is identical. So these 14 ways of arranging lattice points, it is called as Bragg lattices. So according to, we have the following crystal lattices. One is a primitive lattice, second one body-centered lattice, third one face-centered lattice, and the fourth one base-centered lattice. In any crystal, these 4 only possible. So what is primitive? If you take a unit cell, at 8 corners, 8 lattice points are there, then it is called as primitive lattice. Body-centered, in addition to these 8 corners, exactly at the center of the unit cell, one more lattice point is there, then it is called as body-centered. And the third category is face-centered, along with all 8 corners, exactly at the center of each face. It is represented by a pink ball, you can say. In 2 dimension, it can be shown like this only. So this is called as 6 faces are there, and 6 face center points, lattice points will be there. This is called as face-centered lattice. And one more is base-centered. In addition to all the 8 corners, exactly at the opposite faces, at the centers, you have 2 lattice points. Then it is called as base-centered. So these are the 4 fundamental lattices possible in all crystal systems: primitive, body-centered, face-centered, and base-centered crystal lattice. So according to Bragg, there are only 14 ways of arranging these lattices among the 7 crystal systems. They are called as Bragg lattices. So if you take a cubic crystal, in cubic 3 are possible: simple cube, body-centered cube, and a face-centered cube. So these are the 3 possible in cubic crystal structure. If you take tetragonal, in tetragonal, simple structure is common. Simple tetragonal and body-centered tetragonal, they are possible in tetragonal structure. If you take orthorhombic, in orthorhombic, all 4 are possible. So simple orthorhombic, then face-centered, base-centered orthorhombic, body-centered orthorhombic, and face-centered orthorhombic, 4 are possible. by satisfying this condition. So 4 crystal lattices are possible, Brevets lattices are possible in orthorhombic structure. Next, coming to the monoclinic. In monoclinic, a simple monoclinic is common. At 8 corners, 8 lattice points will be there, and it has a base-centered crystal structure also. So 2 are possible in monoclinic. And in the remaining 3, triclinic, rhombohedral and hexagonal, only simple structures are possible. So if you count all this, it comes to 14. So there are 14 ways of arranging the lattice points among the 7 crystal systems, and these are called as Brevets lattices. So this also you can represent in terms of a table, like describe Brevets lattices. If you get, then you write a cubic, a tetragonal, orthorhombic, like that. How many are possible? PIF possible in cubic crystal. Then you must write the condition: A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90. And you need not draw each and every circuit, only simple structure you should draw, and also with examples. In the table you can write, or in the paper separately for each crystal system you can write. Then I think it will be sufficient. So these are 2 important questions in this. One is 7 crystal systems, and the second one is Brevets lattices. Any doubt in this, students, please? Boys, respond. Shall I proceed? Somebody respond, please.
Yes, sir.
Okay. Okay. So this is a cubic crystal system. It is given in detail. Here in the exam point of view, I think it is not required. What I have explained, the same is represented here. Tetragonal system, how many are possible? It is clearly given in the PPT. Only you draw simple structure. No need to draw each and every structure. But for any crystal system, draw the simple structure and mention the lattice parameters, the relation between alpha, beta, gamma, and also ABC with example. It will be sufficient. And next, coming to the lattice crystal is made up of a large number of parallel equidistant planes passing through the lattice points are called as lattice planes. It is a 2-dimensional. So the perpendicular distance between 2 adjacent planes, it is called as interplanar spacing. So the perpendicular distance between 2 planes, adjacent lattice planes, it is called as interplanar spacing. And you have another important concept in this crystallography, which is Miller indices. Actually, if you take any crystal system, the orientation of plane may be in different ways. The orientation is from left to right or from right to left. Sometimes it is diagonally from left to left or top to bottom, like that. There are n number of possible ways are there. But in a real crystal, only one orientation of a plane will be there in the crystalline lattice. So how to identify or how to designate the orientation of a plane in a given crystal? For that, Miller gave a method. So he has introduced 3 smallest possible integers, HKL, which have the same ratio as the reciprocals of the intercepts of a crystal plane having on the crystallographic axis. So this definition you should by heart. So Miller indices are the smallest possible integers which have the same ratio as the reciprocals of the intercepts made by a plane on the 3 axes. So there are certain rules for finding Miller indices. So first, what you should identify? First, we should identify the intercepts made by a plane on the 3 axes. So where it cuts y-axis, z-axis, and x-axis. First, you should identify. Then you should take the reciprocals of these intercepts. After taking the reciprocals, you clear the fractions. How to clear the fraction? You take the LCM and you multiply each and every reciprocal with that. You will be getting small 3 numbers, lowest terms, which are called as the Miller indices. So only this. First, you should identify the intercepts, then take the reciprocals, then clear the fraction. It can be done by taking the LCM and reduce it into lower terms. So these are the rules for finding Miller indices. So simple example, if you take a simple plane, the intercepts made by a plane on the 3 axes are 2, 3, and 2, let us assume. Then first you have identified the intercepts. Then you should take the reciprocals. They are 1 by 2, 1 by 3, and 1 by 2. Then you take the least common denominator is 6, multiplying each and every reciprocal with this, you will be getting 3 to 3. So the Miller indices in the plane are 3 to 3. If you see these 3 to 3, you can identify this plane cuts x-axis at 3 units, y-axis at 2, and z-axis at 3. Like that, Miller indices can be used to identify the orientation of a plane in a given crystal. So it may come as a short answer generally. Sometimes they are clubbing also. What are Miller indices? I did some question in the part B also. But I think definition for Miller indices, rules for finding Miller indices you should represent. And these are the important features. I think just you go through this, you can understand. I'll give some examples for this. See, so certain planes. So let us take a shaded one. You want to find out the Miller indices. So if you see this one, this plane is making intercept on x-axis and parallel to y and z axis. So the intercepts are, it cuts the x-axis, so it is 1, and the plane is parallel to y and z axis, though it cuts at infinity. So the intercepts are 1, infinity, infinity. Then you should take the reciprocals, 1 by 1, 1 by infinite, 1 by infinite. Then finally you will be getting 1, 0, 0. If you see this plane, once by seeing this 1, 0, 0, you can easily observe that that plane cuts x-axis and parallel to y and z axis. Like that, there are a number of diagrams, model examples are given. You go through these examples. These are different sets of planes. Just you go. These are 0, 0, 1 plane. If you see this 0, 0, 1 plane, you can easily say that the plane is parallel to x and y axis and making intercept on z axis. Like that, you can identify the orientation of a plane on a given crystal axis. And this one, you should identify you write an expression for the interplanar spacing. Sometimes you are getting this question. Just to explain in brief. So as I discussed, the perpendicular distance between two adjacent planes, it is called as interplanar spacing. So if you should find out the interplanar spacing for an orthogonal system, you can take it for a cubic system. Further, let us consider a plane, and a plane is making plane ABC. Here you can see a plane ABC. It is making intercepts A by H, B by K, and C by L on 3 axes, and HKL are the Miller indices. So you can identify. Now what you should do is, from the origin you draw a normal ON on this, then it is passing through the origin, and this ON, this normal, it is a normal, it makes an angles alpha dash, beta dash, and gamma dash with XYZ axis respectively. And let us assume another plane is passing through the origin, and one plane is ABC. So definitely this ON, the perpendicular distance, it represents the interplanar spacing, because the perpendicular distance between two successive planes, adjacent planes, it is called as interplanar spacing. So one plane is passing through the origin, and another one is ABC, which is making intercept A by H, B by K, C by L on the 3 axis. Now ON is a perpendicular drawn from the origin to the point N as shown in the figure. This is D, and it is the perpendicular distance, so that D represents the interplanar spacing. So from the geometry, you can write, this is the same figure I have repeated here. From the geometry, you can write cos alpha dash is opposite side by adjacent side. That is D by A by H. Similarly, cos beta dash, cos gamma dash. And from the law of direction of cosines, you can have cos square alpha plus cos square beta plus cos square gamma is equal to 1. Then you substitute this. From this, you can write D by A by H whole square plus D by B by K whole square plus D by C by L whole square is equal to 1. By simplifying this, you can write D is equal to 1 by H by A whole square plus K by B whole square plus L by C whole square to the power of half. This is for a general orthorhombic system. And you consider another plane which is making intercepts 2A by H, 2B by K, and 2C by L. Then you will be getting the interplanar spacing D is equal to 2 by something, 2 by H by A whole square plus K by B whole square plus L by C whole square whole to the power of half. This difference, OM minus ON, will give you the interplanar spacing. So if you do that one, you will be getting D is equal to 1 by H by A whole square plus K by B whole square plus L by C whole square whole to the power of half. This is for a general orthogonal system. If you take a cubic system, A is equal to B is equal to C. So you assume A is equal to B is equal to C, that is equal to A. Then you can write D is equal to A by root of H square plus K square plus L square. So this is the expression for the interplanar spacing, where D is the interplanar spacing, A is the lattice constant, HKL are the Miller indices. So if you identify Miller indices HKL, and if you find the interplanar spacing, then you can calculate A. Once you calculate A, other lattice parameters can be calculated. So this is the expression for the interplanar spacing of a cubic structure. Suppose if you get this question with the diagram, you should explain. First, ABC plane you should identify, then ON normal you should draw, then you should obtain from the properties of a triangle cos square alpha dash, cos square beta dash, cos square gamma dash, then law of cosines you should take, and consider another plane you can write in the similar ground. Take with this difference will give you the interplanar spacing, and you reduce it to a cubic structure. D is equal to A by root of S square plus K square plus L square. So this is the expression for the interplanar spacing. Shall I explain Bragg's law? I think it is there in your intermediate. Students, what to suggest? Students? Girls? Somebody respond, please.
No, sir, not required, sir.
Not required. Only Bragg's law will explain. Generally, Bragg's law, 2d sin theta is equal to n lambda. It is the equation by which you can identify the lattice parameters, because 2d sin theta is equal to n lambda. Lambda is the wavelength of X-rays, n is the order of diffraction. If you could be able to find out the angle of diffraction, theta, then by using this relation, d is equal to n lambda by 2 sin theta. So d interplanar spacing can be calculated. Once interplanar spacing is calculated, you can calculate the lattice constant. So this this is very this is a breakthrough in crystal study of crystal structures. This Bragg's law. There are many techniques are there. Among the important technique is the Porter technique or Debye-Scherrer method. So Porter technique, this is the diagram. Porter diffraction technique is used to find out the interplanar spacing of a given crystal. Generally, many crystals are available in the Porter form, and this technique, it is a standard technique by which you can find, identify, you can calculate the interplanar spacing. So here the principle behind this method is a Debye-Scherrer chimera. So actually, X-ray Porter diffraction technique, it is a primary technique which can be used to identify the crystalline structure. So it consists of a source of X-rays. It is at point A, and these X-rays are allowed to pass through a filter. So a filter, it allows only one particular frequency or wavelength of X-rays. So X-rays are becoming monochromatic after passing through the filter. Then these X-rays are allowed to pass through a series of slits so that they made sharp without any deviation. They can strike the target. And here a Debye-Scherrer chimera is there. It is a stainless steel chamber, a semi-circular, you can see circular chamber is there. It has two holes. One hole is for the X-rays to entry, and another one is X-rays to exit through this. And at the center of this camera, photographic film is wrapped around this stainless steel chamber, as shown in the figure. In those days, only camera film is used, and at the center of the camera, sample holder is there. It is a movable sample holder on which the given crystalline powder is taken in a glass fiber. It can be rotated. So on the sample holder, this glass fiber is placed, and initially X-rays, after passing through a filter, become monochromatic, and they are allowed to pass through these slits. They made sharp. Then they are allowed to incident on this crystalline powder, which is placed at the sample holder. Here in this powder, there are millions of crystals are there which satisfy Bragg's equation. That means when they scatter, there is a possibility of a constructive interference as well as a destructive interference. And when constructive interference is taken, it follows Bragg's law. So it is recorded. It forms like a cone, and it is registered on the photographic plate. After scattering, these X-rays are scattered and they are registered on the photographic film. And due to the narrow width of the film, a part of this cone is recorded, registered on the photographic film, like that. And show in the next slide, like that it is given. And for different orientations, the film is developed and the distance is measured. And from the distance, you can calculate theta. The relation is theta 1 is equal to 90 L1 by pi d, where L is the distance for the first plane, first set of planes. D is the diameter of the cylindrical film, so that you can calculate theta 1. Like that, you can calculate theta 2, theta 3, etc. So once you calculate theta angle of diffraction, using the relation 2d sin theta is equal to n lambda, d can be measured, because lambda wavelength of X-ray is known because it is a monochromatic X-ray, and order for first order n is equal to 1, second order n is equal to 2, like that. And theta is from these values, you can calculate theta. Once you put in this expression, you can calculate D. So if you have the value of D, if you know the Miller indices, you can calculate the lattice parameters. Only you should write this method. So border diffraction technique is a standard technique which can be used to determine the interplanar spacing and structure of unit lattice parameters for the unit cell. So first you should write the construction diagram. You should draw the diagram and construction. So initially X-rays from a source are allowed to pass through a filter. They become monochromatic. Then they are allowed to pass through slits S1 and S2. They made short. So these sharp monochromatic intensified X-rays are allowed to instant on the powder crystalline form, which is placed on the sample holder. So Debye-Scherrer camera, it is a stainless steel chamber which has 2 holes. One is for the X-rays to enter and another one for X-rays to leave. And a film, cylindrical film is wrapped around the steel chamber so that it can take the X-ray record and X-ray diffraction. At the sample holder, you can place the given microcrystalline powder in the sample holder in the glass fiber. It can be moved, and initially once X-rays are instant on this powder, they get scattered, and there are at certain glancing angles, the scattered radiations are in phase. Constructive interference takes place. They satisfy Bragg's equation. So once it makes an angle theta, it scatters with a semi-vertical angle 2 theta, like that. Number of cones are produced, and they are registered on the photographic film. So due to the narrow width of the film, only a portion is recorded. And by developing the film, by measuring the L1 values, you can calculate theta. Once theta is calculated using Bragg's law, you can calculate the interplanar spacing. This diagram also you should draw like that. The powder diffraction method is used to determine the interplanar spacing and the lattice constant of a given crystal. So these are a few applications of powder diffraction method, interplanar spacing, study of mixtures, and different alloys are present in the crystal. They are also determined. State determination in crystals. All these are the applications of this powder diffraction method. So these are the top 3 essay questions you may get. 7 crystal systems, Bragg lattices, and powder diffraction method. And short answers may be the definitions: space lattice, basis, and unit cell. Sometimes Miller indices or Bragg's law. So this you should read in this chapter. So any doubt? Yes.
Sir, short note on Bragg's law on X-ray diffraction means what we should write, sir? Only
Bragg's law. Bragg's law. What actually Bragg's law? Importance of Bragg's law. So
long question, sir.
That's what entire Bragg's law with the derivation. Powder diffraction method means you should write a Debye-Scherrer camera. So after what actually the importance of Bragg's law and derivation for Bragg's law you should write. Got it? So any doubts in this, students? Shall I go to second chapter, crystal defects?
Sir, for long answers, what size we have to write the answer, sir? How many lines?
You should write the answer. It's no, you can't. It count. It depends on student to student. But this, what I have explained, to be represented. Whether you make it number of sentences. If you take 7 crystal systems, it's in a simple table, you can represent. Isn't it? Some students will be writing all the cubic crystal, and they write like that in page wise. Filling the pages is not as important as such. Content should be there. There is no hard fast rule, but 6 marks means at least 5 to 6 points with proper diagrams like that to be represented in the answer. Any doubts in crystal defects, students?
No, sir.
Crystal defects, I think, any doubts, students?
No, sir.
Okay, girls, Somebody respond from girl side?
No, sir.
Okay. And in band theory of solids, chronic mini model, that PPT is sufficient actually. Have you gone through that?
Sir, any long answer questions from crystal defects, sir?
There are three long answers. Na? One is the Schottky defects in metals, Schottky defects in ionic crystals, and Frenkel defects. Actually, crystal defects, there are four types. Na? Point defects, line defects, surface defects, volume defects. Again, point defects, they are classified into vacancies, interstitials. Then you have compositional defects or impurities, fourth one electronic defects. So again, in this point defects, they are Schottky defects. An atom will be missing and goes to the surface. So a vacancy is created. So how many vacancies are created using this thermodynamic relation? What I gave in the derivation, you should write. You may get question, derive an expression for equilibrium concentration of Schottky defects in metals. Sometimes equilibrium concentration of Schottky defects in ionic crystals. Only metals, once you get the derivation, the same exactly two factor will be coming because it is a cation, sum of cation and anion. So only that small change in the entire derivation, only that occurs. If you prepare for one metals, you can easily write for ionic crystals. And the Frenkel defects, it is a combination of both, creation of a vacancy and occupying an interstitial site. So you should identify the number of ways vacancies are created and interstitials are created. Then first entropy, S is equal to Kb log P. Then you using Stirling's approximation, you simplify that. Then at equilibrium, dou F by dou N at constant T is equal to 0, differentiate partially. You can write small an expression for an equilibrium concentration of Frenkel defects. After that, you have these dislocations also. So line defects or dislocations, screw dislocations, small definitions. They may sometimes give for 3 or 4 marks. You should define what is eddy dislocation and screw dislocation, Burgers vector. So it gives the magnitude and direction of the deviation produced in the given crystal along a line is a Burgers vector. So that you can write. So mainly these three will be coming in crystal defects. One is sometimes they put some ambiguity. They have an expression for Schottky defects or equilibrium concentration of Schottky defects. You will get confused whether to write for metals or ionic crystals. If that is the case, generally you prefer ionic crystals. Okay.
Sir, if they not mentioned, we have to write ion, sir, in Schottky defect.
Yeah, that's what ionic crystals. Generally has to mention because it is there specifically in the syllabus. Schottky defects in metals and ionic crystals, it has to define. Otherwise, your student will get the advantage. Even you write for metals, nothing wrong. Yes, any doubts, students? And in this, you have semiconductors also, now. Band theory.
In unit 2.
Tell.
In unit 2, we have, sir, semiconductor.
Yeah.
And
band theory.
Dielectric material.
Chronic. Any doubts in those in the unit 2? No doubts? You have to go through the unit.
Sir, in Cronpenny model, in textbook, they have given 5 points, sir. Those 5 points and the importance, it's enough, sir. Yeah, that's it. First, you should define what actually the failure of why band theory. You should first in the chronic penny model is why solids are classified into conductors, semiconductors, and insulators is not explained on the basis of free electron theory.
So band theory is introduced. According to band theory, the electron possesses periodic potential in a given crystal. That point you should mention. Then chronic Penny model is used to classify the materials as insulators, semiconductors, and conductors using band theory. That you should write. Then it is the propagation of an electron is in this form of series number of infinite potential square wells like that. So minus a b. So whenever the electron is at the site of positive ion, the potential is taken as 0. In between, the potential is maximum. So the potential will be changing from minima to maxima, maxima to minima. You can imagine a number of infinite square well potentials. That you should write. Then Schrodinger's equations, because there are two regions. The potential is maximum, the potential is minimum. So the Schrodinger equation for minimum potential, that is V is equal to 0. Schrodinger potential for maximum potential, that is V is equal to infinity. So that you should write the Schrodinger equation. Then you write the final expression using boundary conditions, applying Bloch's theorem. Finally, we will be getting P sin alpha A by alpha A plus cos alpha A is equal to cos K. Then you should plot a graph. So in the figure, if you see that in the right hand side there is a cos term. So only those values of alpha A are permitted in LHS, so that the entire equation is between -1 to +1, because all are not possible. So alpha A value is only chosen in such a way that the LHS of the equation should lie between +1 and -1. If you plot a graph by cos alpha A and P sin alpha A by alpha A plus cos alpha A, you will be getting that model. Then those 5 points, what you said in the textbook, you mentioned that I gave in the PPT also. You write that one. No need to derive all this because only salient features of chronic Penny model should write. Any doubt in this chronic Penny model? Students?
No, sir.
Semiconductors, I think only these two you should. Concentration of electrons, concentration of holes, you should practice those two derivations. Hall effect also sometimes you may get Hall effect, you prepare well for a Hall effect. When a current carrying conductor is placed in a
transistors.
Yes?
LEDs and transistors.
Transistor is not there in the syllabus, man. Transistor is not there. Thermistor, I think. Thermistor is light emitting diode.
Yes, sir.
Light emitting diode is similar to that semiconductor laser. In the laser chapter, you have that it is a PN junction diode which is operated in the forward bias arrangement. You may get for 5 marks that one. Only that description you should write. For LED, you know that now. So it is a PN junction diode operated in the forward bias. A combination of electrons and holes takes place in the junction region, and this recombination is comes in as an optical power output, and all these conditions.
Sir, derivations are sir. Hall coefficients of P.
Hall coefficient. Derivation Hall coefficient is chadavali. You should read all this. Hall coefficient. So semiconductors, these are important. Concentration of holes, concentration of electrons, LED, thermistor, Hall effect. This you should write. Any doubts in semiconductors and PN junction? All this just you go through PPT, and in manual you have done that experiment also. That you write that.
Sir, what about numerical problems, sir?
Numerical, hardly you will be getting in part A. That also like a de Broglie's wavelength sometimes like that. In semiconductors, I don't think so. Whether you will be getting a short answer for 2 marks. Anyhow, choice is there now this time. Only simple problems, slide. Yeah.
Sir, classroom lo previous year question papers pedtara sir.
Petna kada already apni no. We Google Classroom lo share chesna long back. మళ్ళీ ఒకసారి చేయమంటే ఒకసారి వెతికి చేస్తాను. ఆల్రెడీ ఐ హ్యావ్ షేర్డ్, ఐ థింక్, ఓల్డ్ పేపర్స్. మీరు చూడండి కావాలంటే గూగుల్ క్లాస్ రూమ్లో ఐ హ్యావ్ షేర్డ్. ఎనీవన్ can you tell? I have shared, I think.
Yes, sir.
తీసుకోండి మీరు. I have shared already. And dielectrics for trend important, two important questions.
Previous year's main paper sent, sir. Only supply paper is there, sir.
Main paper is not there?
No, sir. Just again 2019 and 2018 is there, sir. But 2020 only supply paper is there, sir.
Main paper. You మీదే కదా మెయిన్ పేపర్ అంటే 20కి మీరే మెయిన్ పేపర్, అది ఇంకా అవ్వలేదు కదా. You have to write that paper. Got it? Your batch is 2021, na? So in dielectrics, sharing bridge method and types of polarization, two essays are there, and the remaining are all frequency and temperature dependent. Sometimes they may ask, you can't say. Only the ferroelectricity also sometimes. A short answer, right? A short answer on ferroelectric hysteresis. So in general, types of polarization and sharing bridge method you will be getting. And the important questions we have shared that only to pass the exam. Don't assume if you read all those 10 questions, you will be getting full out of full is not correct. So those who can, if you read those questions, definitely you will be scoring more than 70 to 80%. Not complete, because you can't predict the examiner how he gives the paper is also one important aspect. Tomorrow, actually, my schedule is from 11 to 12. I have a meeting. If you are interested, I will take 10 to 11 and I will cover 2 more units. Like if it is you ask me, like superconductors, magnetic materials, and lasers, fiber optics, like that. Electromagnetic theory, and that also very important. If you want, what to say? It's of your interest. Tomorrow, shall I take my class from 10 to 11? Actually, it is scheduled from 11 to 12, but I may not. If you ask me, I'll take from 10 to 11. Otherwise,
sir, 4 units is enough to complete for some exams, sir. 4 units.
5 units, there are 5 units.
4 units సరిపోతాయా అని అడుగుతున్నాను సార్.
మాక్సిమం సరిపోతాయి, కానీ ఇంకా ఛాన్స్ తీసుకోక ఎందుకు మళ్ళీ. కొన్ని ఇంపార్టెంట్ అయినా సార్, వేరే దాంట్లో కొన్నైనా చదువు, అది నేను చెప్పేది. ఆ పీపీటీ చదువుకుంటే అదే నోట్స్ పాస్ అవుతారు, మార్కులు కూడా వస్తాయి. Yes, anything else for today? Tomorrow shall I take class or not? You didn't say. What? Class representative. Shall I take the class tomorrow, or if you want class, you contact me so that I'll arrange the class. Isn't it? Because I don't want to waste, because you have to read many papers now.
Okay, sir.
You inform me, huh? Right.
Okay, sir.
Right. Thank you. All the best.
Thank you, sir.
Right.